Hello everyone. In the last module, we had looked at the concept of thermal resistance for a plane wall with one convective boundary condition on this side and one on the other side, and we introduced the concept of thermal resistances here, and we said when you have multiple resistances which are in the direction of heat transfer, which across the same across various across temperature differences T infinity 1 and T infinity 2, you are going to add them and treat them as resistances in series. So, this is like an obstruction to this heat transfer. So, if I have a very poor convection, if I have air on this side, for example, if I have air here, H is very small. Okay. So, the resistance to heat transfer is going to be very large, okay, 1 over H. So, for example, H water is greater than H air, right. So, 1 over H water is less than 1 over H air. So, if I have water on one side and air on the other side, so resistance to convection here is water side is less than resistance to convection on the air side. So, this is an important thing that we need to remember, because later on in fins we will see the fins are usually added. Fins are basically extensions which are used to improve the heat transfer. You will improve the heat transfer on the part where the resistance is going to be large, so that you reduce the resistance. So, you will use fins on that side. Similarly, if you have say natural convection or forced convection. So, if I have air and you have in one case forced convection, in other side you have natural convection. So, this H forced is greater than H natural, which means 1 over H forced is less than 1 over H natural, which means R forced is less than R natural. So, when I have forced convection, the resistance to heat transfer is lesser compared to natural convection, which means if I have to use this fins to improve the heat transfer, I will add them to the side where there is natural convection. The lower heat transfer coefficient side is where I would want to enhance or improve the heat transfer. Okay. So, now we will go to the case of a composite wall. Composite wall basically refers to a wall with multiple medium or materials which are going to be there. So, let us take a look. This is one, second material, and let us say I have a third material which is this. So, this is if I have A, B, C, let us call it. So, this is T S 1, T S 2, H 2, T infinity 2, H 1, T infinity 1. This is L A thickness, this is L B, and this is L C. These are the thicknesses. 3 different materials. So, thermal conductivity we will say it is K A, K B and K C. 3 different materials are there, and if I were to say that T infinity 1 greater than T S 1 greater than T S 2 greater than T infinity 2, which means the direction of heat transfer is this. Q is flowing from left to right, and my coordinate direction is going to be this way. This is x, and this is x is equal to L is here. Okay, so, let me put my arrows for convection. There is no reason for you to put any other ways, upside up or down arrows, both are okay. So, having specified this, what are we trying to see? We want to find out the thermal resistances for this composite wall. Okay. So, we learnt Q is equal to delta T over everything else, we will call this as resistance. Okay, and we did it for a single wall, we are now going to extend it for multiple walls. Remember one thing, at steady state Q through material 1 is same as Q through material H2 is same as Q through material C is same as Q convection, correct. So, Q is equal to H1 T infinity 1 minus T S 1, sorry I forgot the A, let me write A S into T infinity 1 minus T S 1, which is same as H2 A S into T S 2 minus T infinity 2. These are the two convection terms. Now, which is the same as T S 1 minus T 1 divided by this into K into A S K A by this one, which is T 1 minus T 2 K B A S by L B is equal to T 2 minus T S 2 into K C A S by L C. What are these? This is T 1, this is T 2. So, whichever object or whichever region I am looking at, the heat transfer Q is the same, because we are talking of steady state. So, it is the same Q which is there, whatever comes in here is going through this, is going through this, is going through this, is going out. Okay. So, if I write everything in terms of delta T over the resistances, I would get exactly what I had in the previous slide, which is this way. So, I am going to write this for 5. So, how many resistances I will have? 5 equations for the same Q. I would have 5 resistances. So, let me write them here. Okay. So, to have a little bit of color. So, this is T infinity 1, T S 1, T 1, T 2, T S 2, T infinity 2. This is my direction of Q, and my resistances are 1 over H 1 A S, 1 over H 2 A S, L A over K A into A S, L B over K B into A S, L C over K C into A S. 5 resistances, and we will say these resistances are across this temperature difference T infinity 1 and T infinity 2. So, I will say Q is equal to T infinity 1 minus T infinity 2 divided by summation of R thermal, which is all the 5 resistances R 1 plus R 2 plus R 3 plus R 4 plus R 5. Please remember one very important thing here. I am just because I have 5 resistances, I need not use everything. What do I mean by that? What I say is, if suppose you had this oven problem, I told you about the oven last class. So, if I have this as the glass door of the oven, and this is your outside air, this is the inside, and the manufacturer tells the thing that this should not exceed greater than 40 degrees. If that is the case, what do you mean? If that is the case, then we are going to say that this one is your anchor temperature, whatever be the outside temperature, this should not exceed 40. That means, I want to anchor this if it is 250 or 200 or 150, this should not exceed 40, meaning I know this as a number. So, instead of doing the thermal resistance across T infinity 1 and T infinity 2, I will say Q is nothing but T infinity 1 minus T S 2, the same Q, instead of adding all the 3, say what did I do? I added these 3 things. Instead of adding all the 3, I just add equation 1 and equation 2. I will get T infinity 1 minus T S 2 is equal to Q into 1 over H 1 A S plus L by K A S. So, I will get only these 2 resistances in picture, this one and this one, and that is the total resistance, because I am considering temperature drop between T infinity 1 and T S 2, not T infinity 1 and T infinity 2. I do not have to write the R convection 2 at all, because this is what I am trying to consider. I hope this is clear. So, just because I can write all the resistances does not mean I need to include. I will include only those resistances whose the the temperature at which is known, that I will use, and then use the resistances across that known temperature difference. If I know this, I have to go from T infinity 1 to T S 2 and use that. If I knew T 2, for example, they will say these, if I have 3 materials, 2 dissimilar materials, you have to have contact. Okay, we will see that thing. So, typically you will have a surface which is like this, and another surface which is doing this. Okay. However well the surface is machined, you would have some gaps here, air, which entraps air. Okay. That gives rise to, air is a very poor conductor of heat. So, you would have a very large temperature drop across air. So, you would therefore use what is called as a thermal grease, which is going to be applied to 2 dissimilar materials, so that there is efficient thermal contact. Okay. What I am trying to say is, this thermal contacts, these thermal grease will become unstable after a certain temperature. So, maybe this might be a bottleneck in some application. So, beyond 180 degrees, this thermal this grease is going to become a useless thing. So, T 2 should not exceed 180 degrees. So, it does not have to be this wall, it is something here, which means I will use T infinity 1 and T 2 and use how many resistances? There is one convection, one conduction, another conduction. Okay. 4 temperatures, 1, 2, 3, 4 temperatures will give rise to 3 resistances. So, Q is T infinity 1 minus T S 2 divided by these 3, because T 2 is here. Okay. Or I could use this part instead, I could use this part. If T infinity 2 was given and T 2 was a constraint, I could use this part alone and say Q is nothing but T S 2 minus T infinity 2 divided by R 4 plus R 5. So, the Q's are the same, how many terms I choose to add decides how many resistance are there. I hope this is very clear. This is very important also. You do not want to generally keep adding terms and say, oh, okay, all the resistances have to be taken because I have so many of them. No. What is the driving temperature difference you are using, resistances between that temperature difference has to be taken. Okay. So, let us just go back to this set of slides here. These are analogies, and this is your thermal resistance convective, this is a single plane wall, this is the idea of total thermal resistance. Now, this is the composite wall which I have used, and one very important thing. So, when this is extremely important, the concept of U, which I am going to explain now. If you see here, this is Q is the delta T, T infinity 1 minus T infinity 4 they have called, it is actually T infinity 2, there is a typo here, T infinity 2 divided by all these thermal resistances H 2 T infinity 2. So, this should be H 2 and A, we will get that changed. If what I am trying to tell you is that this Q, I will erase this here. Q is nothing but delta T over summation of R in general. So, in general, this is extremely important, Q is U A delta T in general, just as we had H A delta T. H A delta T refers to convection, okay, heat transfer coefficient, surface area and driving temperature difference, that is convection, pure convection. This concept is basically telling you U is called as the overall heat transfer coefficient. U. It has the same units as H, watt per meter squared Kelvin. And what is it? This Q is essentially a different way of writing this, delta T over summation of R thermal, right. So, if I compare these two, U A is nothing but, and I just compare this, delta T is the same. So, if I go back to this slide, the delta T is T infinity 1 minus T infinity 2. I am going to write this as U A T infinity 1 minus T infinity 2. I will tell you what this A would be. U into A, some number 100, what are the factors for 100? 100 into 1, 50 into 2, 25 times 4, 20 times 5, 10 times 10, 33.3 times 3. Okay. But if this is anchored, this U A is nothing but summation of the thermal resistances. The thermal summation of the thermal resistances is nothing, is your overall heat transfer coefficient into area. What does this mean? Means is, for a given system, what do I mean by a system? I have a particular geometry, I have chosen a set of, it is a plane wall, multiple materials are there, the dimensions are fixed, the temperatures are fixed, everything is fixed, the problem is fixed, the physical problem is fixed. That means, all these quantities R1, R2, R3, R4, R5 are all fixed, right. If they are fixed, they are constant, that means this R thermal summation is a constant. If that is a constant, reciprocal of that is a constant, which means U times A is also a constant for a given system and flow conditions. Am I right? I am not saying that I add one more resistance, no. I add a fourth block, no. I change this fluid from water to turpentine, which gives you a different H, no. I am not talking of such situations. Having fixed a problem, having fixed the dimensions of these different materials, the values of the heat transfer coefficients which are going to be there, the fluids which are causing that, etc. All I am trying to say is, once these resistances are fixed, the summation is a constant, which means U times A is a constant. Overall heat transfer coefficient times area. What is this area? Just like you had H into A, UA can be based on any of these things. So, I could have UA based on this area, this area, this area, this area. In a plane wall, all the areas are the same. All areas, all the heat transfer areas are all same. What do I mean by that? This is your left wall, this is your area. This is your intermediate wall, that is the area. Third wall, this is the area. Fourth wall, this is the area. And here you have H2 T infinity 2, here is H1 T infinity 1, TS1, T1, T2, TS2, LC, LB, LA, KA, KB, KC. But whatever is changing, these areas are not changing. In a plane wall, so whether I call it U1A1 is equal to U2A2 is equal to U3A3 is equal to U4A4, A1 is equal to A2 is equal to A3 is equal to A4 is nothing but AS. Therefore, all U values are same. Why am I going through this so much when it is all the same? Well, we bring the concept of radial system or cylindrical system. If I have a cylinder, this surface area is 2 pi r L or pi d L, correct. So, I have a water carrying pipe here of length L, diameter is d, area, surface area is pi dl, right. Now, if I want, this is hot water is flowing at at the pressurized water. So, the temperature is 200 degrees centigrade. So, pressurized water. Okay. I do not want the heat to go out. Okay. It is for some process. So, I do not want the heat to go out. So, I am going to put some insulation. So, I am going to have insulation around this. So, this is your pipe. I am going to have a asbestos or glass wool insulation. Okay. So, this is a solid. What is the surface area of this? Pi d2L, where d2 is outer diameter, right. That means, in radial geometry, this can be also taken for a sphere. So, I have a sphere, a spherical flask, I am putting insulation around it, the area, surface area of the insulation will be larger than that of the flask. If I put 2 layers of insulation, that will be different. So, pi dl for cylinder, 4 pi r squared for sphere, surface area formula. Okay. So, surface area is a function of r in radial systems. Very, very important. We do not know what radial systems are, I will tell you that in a few minutes. But if this is the case, then if I want to define UA, so we said UA is 1 over summation of R thermal, which is a constant. Radial systems, what I will write? Inner, if I base it on the inner area, U would be U1. If I base it on the outer area, AO, but both of them are equal to reciprocal of the thermal resistance. Okay. So, if the inner area is, so let us say R2 by R1 is equal to 1.5, let us say. Okay. L is the same. Ratio of U1 A1 is equal to U2 A2, we are talking of cylinder geometry. Therefore, this is nothing but 1 over summation of R thermal, this is a constant, because we have fixed the problem, everything is fixed. So, U1 by U2 is nothing but A2 by A1. For a cylinder, it is pi d2 by d1 into L, cancel d2 by d1, which is 1.5, which means U1 is 1.5 U2. Okay. The values, U is not a constant, U times A is a constant. U is not a constant, U times A is a constant. That is the take home from this. Overall heat transfer coefficient, you will see it again in convection internal flows, you will see it again in heat exchangers, where UA times log mean temperature difference is what is used for calculating the heat transfer in a heat exchanger. Okay. Now, let us go back to what the slides have to say. So, UA is nothing but 1 over thermal resistance, which is Q divided by delta T. We come now to parallel circuits. When will resistance be in parallel? What is this business of parallel? So, if I have let me go to a fresh slide, resistances in parallel. If I have multiple paths for heat transfer across the same temperature difference, multiple paths for heat transfer across same delta T, then resistances will be in parallel. What do I mean? Very simple, I am going to tell you. We will go to the slides, that is not a problem. Suppose I have a wall. This is a heated plate, okay, heated plate. Your electric stove, maybe not the induction type, the electric stove where there is a coil and it is heated. So, this is T wall is much greater than T infinity. So, this is air outside, which is at temperature 25, which we call T infinity. So, heat is getting transferred to the air by two means. What are the two means? One is Q convection, other is Q radiation, right. Temperature difference is T wall and T infinity, the radiation occurs between surfaces. So, let us say this is the wall of the room, the fan, everything in the room, everything is at T infinity. T infinity is the temperature of the wall and the temperature of the air in the room. So, the heat transfer is going as Q is equal to Q convection plus Q radiation, which is H A surface T wall minus T infinity plus, what did we write for radiation? Sigma A surface T wall to the power 4 minus T infinity to the power 4, and this is your emissivity of the surface. We saw this. Okay. Now, let me write Q radiation separately, epsilon sigma A s T w to the power 4 minus T infinity to the power 4, which is sigma A s, this one, T w to the A squared minus B squared form, A squared plus B squared into A squared minus B squared. This I am putting together, I will group all these together. So, this is going to be, okay. What is this? This is like your H. So, I will write Q radiation is H rad into surface area into T wall minus T infinity. Please note, this has no physical basis or anything. This is just a group of terms which have been created mathematically, so that the equation looks like my Newton's law of cooling. So, if I want to put this here, this is H A s T wall minus T infinity plus H radiation into A into T wall minus T infinity, which is what? T wall minus T infinity 1 over H A s. Please note this, do not make a mistake here, 1 over H radiation into A s. The resistance here, convective resistance is here, R convection, this is R radiation, 1 over H A, 1 over H A. Okay. This is, what is this? When do I see this? This is an equivalent resistance T wall minus T infinity divided by R total, where R total is nothing but 1 by R total is nothing but 1 over R convection plus 1 over R radiation. When is this written? This is written when you have R convection parallel to R radiation, right, you know, in your electrical circuit. So, I have like this, this is your wall, T wall, this is my T infinity, this is my R radiation, this is my R convection, two paths for the current for the heat to flow, and finally you get the algebraic sum of these two heat transfer. Remember, this H radiation is not a constant, It is a function of temperature, very strong function of temperature. You have, see, Tw squared plus T infinity squared, Tw plus T infinity, etc. It is not a constant. It is a group of terms which are used so that we can simplify our calculations, especially when we are doing typical convection and conduction problems. When you are going to do radiation, this we will never introduce H radiation business at all. Okay, when you are doing conduction and convection problems in this course, as a part of this course, where radiation has not been introduced and the only thing that you know is this one, then we can sometimes use this idea of H radiation. The point I am trying to make here is, when I have multiple paths for heat transfer across the same temperature difference, what is the temperature difference here? T infinity 1 minus T infinity 2, Tw minus T infinity. You have two resistances which are R convection and R radiation. These will be in parallel because heat has two paths that it can take. One is your convection part, other is your radiation part. Okay. So, with this I will stop this module. We will use the same concept of resistance in parallel to go through what is given in this slide. I will just show you what is there. It talks about the composite wall, except that in this you have two parallel paths for the heat to flow between block E and block H, path F and G, that will be resistances in parallel. And after that we will go through the idea of contact resistance, which also we have seen a little bit. You know, two surfaces in contact, dissimilar materials, you have air trapped in between them, and that leads to a large temperature drop, that is called as contact resistance. Thank you.